Hello everyone, this will be a theoretical video, so combined with diagnostics, but mostly it will be focused on T2 power sequence. So this type of machines is a bit obsolete, but there are still plenty of devices to fix, especially if you need to get data from them. So this will be the first video, like the overview, and I will make a little bit more detailed videos later. Just focus it on some other things in more detail. So here's our WIKI page. I just uploaded the last version of power sequence. This is power and diagnostic sequence. So basically I try to combine everything you've seen in this chart above and this one here into one PDF file with as straight as possible sequence diagram. Okay, so let's talk first about the gear. So what do you need to work on MacBooks generally and to do proper diagnostics? So the first thing is obviously multimeter, so you need a good multimeter. I use Fluke 175. This is my daily use multimeter, so it never failed me, it never showed me some weird values. Obviously you can find the cheaper parts, you can go with Aneng and stuff like that, but they are usually slower, and also when you do some daily jobs you need something which could work as a reference. So around $100 or euros is normal price to get a proper measurement device. Yeah? So the second thing you need is Apple power supply. It's not necessary, it shouldn't be necessary power supply from Apple vendor, but it would be nice if you have it as a reference. Then you can use a simply different, like a cheaper power supply, but always keep a reference somewhere around. So the best one would be possibly 130 watt Apple power supply, because it will power up and it will turn on every possible Mac, even without the battery. So as a reference it's quite important. Same with the cable, you can find third-party cable. You need to test it to check if it works exactly as OEM cable or non-OEM cable, so you just need reference parts on your power supply side. The next thing you're gonna need is power meter. I have a little bit fancier here. This one is called AVHZI. This one. This is a bit expensive, it's around $100 or something like that. Oh, and we see tariffs here. This is something new. Okay, so probably this is for the United States. So you pay 91 plus 84 export tax. But yeah. The cheapest option would be the one from the KVEC. This is like 5 or 10 euro device. So this one, it looks like that, works perfectly fine, but it's just a power meter. So the thing from the AVHZI is that it can show you much more, because say if you need to do a little bit more or a little bit more difficult diagnostics, you actually need this stuff to do this type of measurement, where you can see what is going on with your machine. So you can see here, you can do the whole graph. thing. It shows you basically lots of information regarding how device power ons. For example, here I'm plugging it into the machine. First it has like current spike because it stabilizes PP boost and charges the caps internally. Then you can see how it charges the battery, like with this step ladder upstairs. So this is quite useful here. Obviously you don't have it on small multimeters. You will only have some very basic things, like how much current and what voltage is it. I'm not sure you can see the picture here, but basically it's everyone knows how it looks like. So the next thing, quite useful, is USB-C tester. This one is from Mechanic. This is T824. 8 because it has 8 pins for lightning connector, and 24 because it has 24 connections for the Type-C. So what it does, basically it does diode mode checking of all pins, and it shows you what's happening with your port. Very useful to find if your port has short circuit, if it's damaged, if there are some open lines, if there's no connectivity somewhere. So definitely my recommendation. There's a different type of the device, is a Quanly. This one combines power delivery and USB-C monitoring with diode mode tester. I usually use Mechanic because I find it a little bit better. Also, it turns automatically off, so it won't discharge the battery all the time. But this one, it also has labels of each pin, which might be also useful if you're not that familiar with how is it pinned. This will be helpful. It has a little bit different readings. I mean that, for example, so this one shows in VBOS 0.25, 0.18 voltage drop. This one shows 0.496, which also makes sense because the audio measurement is a little bit different on many devices, so you always need to take take an account that basically there are no perfect values, and if you try to match it, if you see like there's a 50 millivolt difference between one reading and another, between reference and your board, it doesn't necessarily mean something is wrong with your machine, because this is some sort of iPhone type logic, because people who repair iPhones, they usually tend to use more straightforward methods. They simply check everything for any anomalies in diode mode. If something is wrong, they simply dig in this direction. It's certainly fine if you don't have a schematic, if you don't have proper board view, that you need to work like in more blind way. But we have all board views, we have all schematics for MacBook board, so we can do more some more precise diagnostics, because basically if you have voltage drop like 0.2 or 0.4 or 0.8 volts, it's all different types of diodes which are measured, and it's not really that important if you have like 10 or 20% difference. It's not, it doesn't really matter. What really matters if that you can check if it's open line, because that would mean that you have some problem with your circuit, or is it shorted, or if you have like differential pair, like negative and positive. For example, on display aux line, this would, if you have different values, this will definitely mean that you have a bad decoder or bad receiver part in the IC. For example, differential pairs, they usually should be on the same values, so both negative and positive. Okay, so let's go back to the sequence. Here we go. So let's go to where it still starts. So probably we need to disconnect the battery first. So this one came in with no power, and I will also do a diagnostic for this device. I already have an idea what could be wrong with this machine, but I wanted to show you how do we see that using the power diagram, and how do we pinpoint where to look at without checking everything. Because you don't want to like check, for example, the CPU or the GPU resistance if you have problem on some lower level. And same, you don't need to check lower level stuff if you already know that your machine is somewhat closer to being on. Okay. So now the first thing, we are gonna plug the connector here, so the USB-C connector. Let's start the current analyzer and let's plug it in. Okay. So what do we see here? So we see that the 5 volt came up to 20 volts. We see that there was no power consumption before it actually turned on 20 volts, which means that battery is partially charged, which means that it was powered, the machine was first powered from the battery, and then it started to charge the machine. So there was one current spike up to 2.7 amps here, because most likely because the PP bus started charging the battery, and the battery or the stabilizing capacitors needed to be charged. So we have current spike, then we have ladder like step up. So basically what it means when we go back to the sequence, let's zoom it a little bit. So what it means is that we already have all this stuff sorted out. So we have, let's find where do we have the battery. So basically we have the SMC init, we have E2C power, we did main enable, let's find here. Okay, actually I think I might need to edit, because it's I didn't explicitly write that there's a battery charging. But for now we need to look if it's let me see. Yeah, so first we need to look if it's charging the battery, yeah? So if we have the battery charging, we can also exclude at least the first phase of T2 booting, because to charge the battery it needs to read it, and it needs to communicate with power supply. So now, since we see that our power supply is being loaded with 20 volts, 0.6, 0.7 amps, we can conclude that it's charged the battery, but it doesn't turn on. We have the click on the trackpad, so we have 3 and 5 volt regulator is already on. So basically everything should be on. Now it starts trying to load the bridge OS from the SSD and to start the Intel part, and this is probably exactly where it stays. So now let's try again. Let's try the same, but with battery disconnected. So let's remove the battery, and so we'll keep the lid open in case it decides to turn on. Now let's run. Okay, as you may see, this is a whole different story here. So first we see the first initial current spike, then a lower, then once again, one more, then we have 20 volts, and now we are sitting on some like 0.1 or less current consumption, which basically means that battery is not being charged, it's disconnected, but T2 is already booted, and it talked to power supply to switch it to 20 volts, and now it waits for something. So most likely this machine is in so-called recovery mode. It's not the same recovery you get with command R. This is recovery mode regarding iPhone or iPad devices. So this is like booted SoC, which awaits system restore through USB cable. So recovery mode means basically that it didn't find its internal system, so like the second level system, which is Bridge OS here, but it already loaded the low level SoC firmware, which also count LBB. This is LLB, I'm sorry, low level bootloader, which is basically a stripped image of iBoot, which is stored on the SoC ROM chip. Alright, so now let's get a little bit back and start from the beginning. So what's happening when I connect the power supply? So the first thing, we have the CC impedance trigger, which means basically the power supply, as you may see right now, it doesn't output any voltage. So to do so, it needs to see that it's connected somewhere. It is done by measuring the impedance on CC line. So once you connect it, it should have around like 40 or 80 kilo ohms to ground, and this will tell the power supply that it's time to turn on 5 volts. So once we connect it, we see 5 volts, which is used by the machine to power on almost all G3H rails. So what's happening first, the CD3215 or 17 in this case will turn itself on. It will generate some powers, which are LDO3V3, LDO 1.8. These are internal power supplies of the chip. They are used to power up different parts of the chip. For example, there's a power supply which is used to power up CC controller, which talks, or the PD interface, which talks to the charger, which would be on 3215. This would be the LDO BMC. But the first thing CD3215 or 17 does, it allows 5 volts to the system. So 5 volts go to power manager. It's ISL 9240 on all T2 machines. So its job to generate first PP bus voltage, which is 12.3 volts. It will go slightly up once T2 is booted. I can also demonstrate that, and you can see how it rises. So let's put it here. So, and plug in the charger. As you may see, 12.3 volts, 12.6 once again, 12.3, 12.6. What's happened here is that this step, E2C power SLC SDA communication, PP bus will raise to the 12.6, which means that T2 booted it's misspelled here. So it's booted LLB. It started SMC part of it, and it started to talk with charger. So it tried to ping the battery, and it boosted 12.3 to 12.6. So 12.6 means T2 init to low level bootloader is done, and it's stored in SOC ROM, so SOC ROM. Okay. So for now we can actually skip testing all this stuff here, because we already know that if we got here to the 20 volt, if we got here to the 12.6 volt, we know that the machine is at least on T2 level is completely fine here. Let's look into schematic. The next step to check would be the ESL9240. So we are not really checking it because we know it works, but I will just show you some common failure points you need to check if you don't have PP bus. So basically, if you move on the power sequence, once you see that something is missing, you can start looking into checkpoints listed. Let's go here. Okay, let's go with Chrome. So this is our ESL9240 charger. It's quite common. This is the same principle as on older machines. Basically, it's on almost all PC laptops. Modern PC laptops. On older machines there was different power supplies. This scheme is called narrow voltage, which basically means that the system power is approximately equals to battery power. So the first thing happens here is that it senses if there some voltage on the input. So for example, here we have 5 volts. It will be then reduced by charger aux detect. This is these 2 resistors. Basically, this is called charger aux detect. So this is a voltage divider here. So we have 750 kilo ohms and 255 on the lower part of it. So it will yield approximately 1.4 volts in 5 volt, and proportionally more once it's in 20 volts. So after that, it also gets it PP bus power here. The power in goes exactly here. This is from pay in. This is main VCC of the ESL. Once it gets it here, it generates 5 volts for itself. This is VDDA. VDDP is a very important point to check, because basically this is internal power supply for the chip itself. If it's not working, the chip will not be able to run. So here, as you might see, charger VDDA 5 volt internal IDO. If it's 0 volts, you should replace it. So the next thing to check always would be the current sense loop. So the current sense loop is here. So as you may see, we have 0.01 ohm precision resistance. It is used to measure how much current do we have through the machine. It goes to 2 1 ohm resistors, also precision resistors, to CS-in, CS-en, CS-ep. So current sense input negative, current sense input positive. The second loop would be here. This is for the battery consumption, so it's for the battery current. basically the same principle. Very low resistance shunt here, 2 resistors, 1 ohm, and they go here, charger CSO, CSON. So this is current sense output positive, current sense output negative. So these 2 loops are often being burned, for example, by bad power supply, or if you have bad ESL 9240, this might also fail. So basically, to sum it up, on the ESL, I would say 90% cases where you don't have the PP bus, but you have input 5 volts here, that would be either the current sense input, current sense output, or failed chip itself with a lower VDP, VDDR, a power supply. If you have 4 volts, something 4.2 or 4.4, it's still bad, it's low, it should be 5 volts, exactly 5. One more thing about how exactly PP bus voltage is generated. So as you may see here, this voltage here goes straight to the cell pin. Cell pin is, if you fixed PC laptops, you know that the cell pin is here to show the power controller how many cells in series do you have in your machine. So basically, if you have wrong voltage here, you might have wrong power, so PP bus voltage. I had a machine where charger was partially broken. There was 4 point something volts here, and PP bus was 3.8 volts instead of 12. So most likely it was caused by partially broken internal LDO supply. It was enough to run the chip, but it wasn't operating properly. So replacing this chip obviously fixes this issue. I think it was in my raw video. I think it was raw video 4, if I recall. Okay, so let's sum it up once again. You have no PP bus, you look in this area, you check here if you have 5 volts. If you have 5 volts and this one here is fine, not broken, so you measure it here on the capacitor closest to the ESL 9240. If you have bus loops fine, you basically need to check if you simply to replace this chip and to check if it goes any better, because this is not rocket science to resolve PP bus. I believe I never seen one of these chips failed. Sometimes I almost sure that they are failed, because there's interesting thing about ESL 9240. Sometimes it leaves some residual charge on gates if you remove it, and once you measure this thing, instead of having it discharged, you will see that they are kind of shorted, but it's not, because you need to first discharge them completely, then you can measure, because if your gate is charged, this will conduct, this will allow voltage through, and you will see some like 2 or 3 ohms resistance, which is obviously absolutely fine if MOSFET is partially opened. So this is very unlikely to fail. Sometimes this one might be failed. So this is a butt FET. You will see it by some weird anomalies with charging, like it will charge battery if the device is off, but won't charge if the machine is booted to the system. But this type of failure is really rare. Okay, so that's it for the PP bus supply. So once you have PP bus 12.3, we can move further. So now we're up to the next very important step. This would be charger enable MVR. This one generates PP3V3 GTH RTC line, which is then bypassed through the CalP PMO to the 3V3 GTH, because GTH is powered a little bit later. Even if you have it, it doesn't mean that the power supply of the GTH is active. So let's check what I'm talking about. So once again, let's go to schematics. So this is charger enable MVR. Let's go to the board view. So it goes from ESL 9240 straight here to this small power controller, which is the same as used for 2.5 rail power supply for SSD. It's also seen on many machines like on A2442 as a 5-volt power supply for the right USB port. This is not a good chip. It fails quite often. It doesn't like any humidity nearby, so it dies really often in all rolls. I mean, it dies if it's used for the 5-volt rail to the output devices. It dies if it's used for SSDs, often killing the SSD. And but as I already mentioned, Apple is very traditional, very conservative. They don't really replace chips unless it's absolutely necessary. So if they have some chip in their production line, they will stick to it many years. So this one is on machines, I believe, since 2018, and I think I've seen this chip on even M4 Max. I'm not quite sure, but it wouldn't be any wonder if it's still used. So now let's go further. So basically this chip can be configured, so it has a feedback line. So this voltage divider on the feedback line basically sets the output voltage of the chip. So it's quite universal. It can output different. We also here basically you can see they even put the formula to check or to tune the output of the chip. So you can basically change the resistors here, and you can change the voltage. Okay. So now we have let me see. This is our face. Feedback. Output. And there should be, no, this is the voltage in. Let's go here. So this is our RTC line, which powers up some stuff on the board. But most important point is here. The small resistor goes straight to the CalP. CalP is the PMIC 42. So let's look here. So we have the 0 ohm resistance here. It goes to here V in RTC. So this one is CalP here. The PMU for the T2. It goes here. And it goes out here, V out RTC. And this one is PP freeware free GTH SOC PMU. So this power rail is actually connected to the main GTH line. So as you may see here, this is PP freeware free GTH. The same as here on this power supply. So to sum it up, before T2 is booted, the free P3 GTH power supply, this one, is substituted with GTH RTC lines, but these are different lines. So basically it bypasses power supply the freeway-free GTH RTC to the freeway-free GTH. Because for the lower stage we don't need that much power probably, and it will later change. So say if we have a device in DFU mode, let me demonstrate that. So let's put the machine into the DFU. Once again, the most reliable method, you press the DFU button. It's not really a button, but here let's search this part. Button for the fourth DFU. So it's located right there. So we press the button with tweezers because we don't need to solder it. And now we are putting machine to the DFU. So I connected the power supply. So the first thing this device seen was DFU. Sorry, it was not connected properly. So now you can see that we have different power consumption. We have 5 volts, almost 0 amps. And let's go further. So the trackpad doesn't click. Let's look at our power rails. So now we have 3.3 volts from the RTC. And now let's check if we have free V3 GTH. It's also there, but there's no 5 volt rail. So here, look at that. So here's our GTH inductor. It's here. So we have 3.3 volts, but it doesn't come from this inductor. It's not there because basically we don't have VDD enable. So there's PMU VDD enable signal, which comes from the Calampi PMIC, which turns on this chip. So it turns on 5 and 3 rail, 3 volt rail. So it's a little bit hard to measure here on this side of the board, but there's no enable right now. Once we have enable on the chip, by the way, we have 5 volts, and the 5 volt, and once trackpad gets 5 volt, it starts to click. So this is how you know if you have T2 booted or not. If you have no click, you can be sure that T2 is either in DFU mode, or maybe it's there's something wrong with its power supply, because there was no one to say to yield enable signal to the chip. Okay, so now let's go a little bit back. Let's step back now. We are unplug it and plug it normally. Now we have 3.3 volt GTH, and we have 5 volts, and we have clicking trackpad, so it clicks now. So to click trackpad needs only 3 conditions. It needs PP bus input for the coil. It needs 5 volts for the main power supply of the click controller or for the trackpad controller, and it needs lead open signal to know that machine is not closed. These are just 3 things it needs to click. On newer machines, on M2 machines, they changed the firmware, so now it doesn't click per default. It waits till system boots a little bit and sends enable signal via SM-bus line to the trackpad. So it's no longer a case for Apple Silicon machines. But on T2, this is absolutely straightforward way to know on which step you are into in this power sequence. Okay, let's check if we missed something. Okay, so now Comp PMU gets power and turns on T2. So we have charger enable MVR coming from the ESL 9240, which means that PP bus is probably fine. We have 12.3 boost. The interesting thing is that charger enable MVR, sometimes it's yielded even if PP bus is not there. So this is 100% the case on the 9239, like on previous Intel, raw Intel machines or T1 machines. I'm not 100% sure it will be the same on 9240, I believe so, because charger enable MVR is probably controlled by different logic. Most likely it will, it will be controlled by aux detection. And once aux detect is fine, it will try to enable 3.3 volt power supply. Okay, so after that we have 3.3 G3H rail, which is then sent to the CD3215/17. Now let's go back to the schematics. Let's check one of these guys here. Now this one is I believe this one is connected to the SoC ROM. No, this is Thunderbolt ROM, I'm sorry. So this one needs G3H RTC here as voltage input. I believe on some machines it used G3H, but I might mix some smaller details. It's not that important at this moment. So let's go to the ROM. So the ROM chip is powered by PP3x3 UPC XB LDO. On this LDO power supply, that's this one here. I believe it's only turned on once it has voltage in 3v3. I'm not 100% sure, but I believe that it's this is the case because it has it's grouped here, so most likely in 3v3 is needed to power up these LDO parts. We can actually check it later by removing the 3v3 enable, MVR enable, simply to check if this would be the case that the device doesn't read Thunderbolt ROM. Not that relevant right now, but okay. So let's get back to this sequence. So CalP sequence, PMO X-Tau, this is a frequency generator. It needs, the chip has internal logic, so obviously it needs clock signal to run. So after it stabilizes all the power supplies for the T2, it will yield PMO sys alive, PMO active ready, PMO called reset L. PMO called reset L is basically reset signal for the T2. So once T2 is powered and it has released reset signal, it will read SoC ROM. If there is nothing on the SoC ROM, or if there are any problem with that, it will fall back to the DFU. Once it reads, it goes to 20 volts, approximately 0.1 amp. It depends on board. On bigger boards they have more caps, so they might spike to the higher values, but it's approximately the same on all T2 boards. So now to make the switch, we have E2C UPC T2 to CD2 321517 power delivery, and it tries to start to communicate with CALPI via SPMI, so power management interface, serial power management interface, seal key data. It talks to CALPI, and now it yields PMO VDD main enable through CALPI, and disables bypass switch, internal switch between G3H RTC and G3H normal. T is here, it can be ignored here. So bypass is now disabled. G3H is now powered by its main power supply. So you have UV3 G3H independently, PP 5V G3S, and you have trackpad click. After that, all G3S power supplies should be raised. There are a couple of other ones, and you have power good. And now we have power sequence for the SSD. So this is exactly where the sync fails, and let's check it. So we have the first SSD PMO reset low should be released, should go high, and we will have some communication with power supply. Let's go to the schematics. Here. So for example, this set. So we have same power supply as for RTC. So you may see this is the same Texas Instrument ALC 180. Absolutely the same chip. It has enable signal. It has this feedback voltage divider, which sets this voltage to 2.5 volts, but this is absolutely the same TPS 62180, which is also one of the most common failure points on 16-inch machines. We also have a bigger PMIC. This one has brain, so this is our PIC color, I believe. This is main power supply for, or power controller for the SSD. So basically this is a chip which yields 2.5 volt enable signal. It also has SCL, SDI, so E2C line, and as you may see, it goes from this chip, it goes straight to the T2. So this is one of the T2 interfaces here. E2C, SSD, SDI, and SCL. It's somewhere there. SDR, SCL. Okay, so now let's check if we have voltages on our SSD power supply. So once again we have 20 volts, T2 is booted, we have trackpad clicking, we have 5 volt rail, 3.3 rail independent. Let's go through all power supplies. So right side, right wing power for the SSD. We have 2.5. Let's check if T2 tries to reset it. So it happens approximately every 20 seconds. This might indicate some problem with NAND. Let's check if it's stable all the time. Yeah, and as you may see, every 20 seconds or so, this one is turned off. Okay, let's check if our other voltages are here. So we have 1.8, we have 0.9. There are 3 power supplies, 1.8, 0.9, and 2.5. Okay, so something is happening with SSD, so it tries to reset it all the time. Now let's check the left side. There's not much points to check if it works, but because the 2.5 is on the other side, but I believe there are some caps on this side. So 0.9 is there. .8 is there. Now let's locate the 2.5 volt for the left side. I think it's gonna be this one. Yeah, 2.5 volt NAND. Okay, and let's check this one. And we found our problem. So we have 0, or not even 0, we have some sort of low voltage here. It has the same cycle, so that's how we know that we don't have to check enable signal, because we know that enable signal also resets itself. So we have 2.5 missing on the left side. So at this point, we can also try to prepare ourselves for the bad news, because most likely SSD is broken or SSD is bad. So now let's turn off the power and let's check the resistance to ground. It's not good, looking good. So the right side resistance, it should be kilo ohms. Once discharged, 60 ohms, but it goes up. So probably there's some residual voltage here. No. Well, but anyway, it goes up, which means that it's most likely fine. It simply charges the capacitors, so it will go up and up and up. So 500 ohms on 1.8 and kilo ohms on 0.9. So right side is all fine, left side is unfortunately bad. So it has 0.2 ohms resistance to ground. So we have 100 ohms here, kilo ohms on 1.8. So everything looks fine. So it's time to remove the board and to check what's happened to the SSD. There are a small chance that it's just a power supply or some cap around which is broken, but most likely we will see that SSD is shorted on this machine. So this would mean SSD replacement. So it's also safe to say that our first part of diagnostics is done. So basically we checked everything up to bridge OS boot, which needs SSD, and now we cover the symptoms. If you have clicking trackpad but no power, most likely you have problem with your SSD, so maybe there's some corruption in the firmware, so you need to restore it. Maybe there's some electrical problem like here, like short circuit. So this one is not lucky, but if I recall, customer basically needs data from this machine. It's not absolutely necessary, but it would be nice to have. But this machine should be fixed in both ways. So this chipset, if I recall, this is 1 terabyte configuration. But we'll check it. Okay. Now let's remove the board and look what's happened on the other side. So now, without even disassembling, we checked actually lots of stuff. and I usually do it as I take the device, as I check the device in, because such steps can be, if you know the sequence, you really don't need much time, like to at least to find the approximate place of failure, like here on this SSD. You have quite a lot of screws in each MacBook. And I really do hope that we have short circuit to ground not via the one of nuns, but somewhere else. We can also look with thermal camera actually. But we get the board out of the chassis first. Thermal camera is, by the way, not absolutely necessary or recommended, but there are some cases, believe me, which are not solvable without the camera, or at least it would take much more time to diagnose without thermal. Because, for example, in case that you have some short on the LDO line, which is not much current, there might be some temperature spike, like maybe 5 or 6 grades above, and if you see some chips blinking like that, it's quite possible that you will find it only with thermal camera. It's not always the case, but quite often. Okay, so we have some water damage on this NAND supply as always. It doesn't look good. There's not much damage, but it was enough. So we have corroded feedback. What gives me hope is that we have corroded ceramic cap. There might be some hope for this machine, because corroded ceramic caps, they tend to short themselves. Oh, we have more here. I'm not sure if it's 2.4, but let's check. 0.9. Okay. Yeah, so we have really low chances of this machine working without SSD replacement. Okay, now let's remove corroded junk, and let's hope we have proper readings after that. Even if NAND survived this shock, it's still possible that we will have corrupted firmware on the SSD part. So we will have to fully restore the machine to get the data to get it working, and there will be no data after the full restore. It's actually the saddest things, you know, like the SSD is fine, it survived, but because of the voltage problems, because of the power problems, it did actually screws up something in firmware or maybe in like system partition, and there's no way to fix it without having access to some development stuff from Apple, which is obviously not the case. Okay, now let's remove caps here, and I'll remove this nasty shit too. Because even if it's not shorted now, it will short later. And as it will short, it might confuse power supply, and power supply may yield higher voltage, killing nuns once again. Okay. Okay. Let's check again. Again, we have a very lucky case here, so as you may see, we have kilo ohms on 2.5 rail now, so it was in fact cap problem. So what we're gonna do now, we're gonna still replace this power supply, or at least we need to reball it, because there was water here and we don't want any risk. If data is important, don't take any chances, don't use this chip, because we don't know what will happen when we turn it on now. Maybe it will try to yield higher voltage, maybe it has some corrosion underneath it, which is most likely the case. So if data is important, you always focus on the question, will it possibly harm the data or not? So for now, obviously running this chip, or running it now, or trying to turn it on, will bring some more risks to the machine, so we will replace this chip. Most likely the original one is fine, but we need data, we don't take any extra risks. Alright, so now let's put it here. And also we need to cancel one appointment. Okay, can't find it. Let's hope it won't disturb much. Okay, let's find our ELC 180. I'm quite sure I had plenty of these, but I can't find one. Let's look somewhere else. Okay, we got one. And let's put it back on board. Now let's find donor board for caps. Okay. Just a few more and we will be ready to test. The most important thing to check first, if we have no connection between PP bus and SSD power. It's very important. Okay, so we don't have any. Let's go and check. Okay, this one is not critical. Let's check feedback. Okay. Also okay. Alright, so now let's clean it a bit and now let's test if it works. I really hope that SSD firmware wasn't corrupted, because it's always sad if you fix it, but you have to restore it. Well, I will not restore this machine because I will try some more stuff to get data from it, but most likely corrupted firmware means lost data. Okay. Now let's check it. Okay, so we have some very weird power consumption now. Let's see if it 2.5 volts is back. Yeah, 2.5 volts is back. 0.0, 1.8. We have very weird state of the board now. Okay, so now we have a little bit more. It definitely tries something. So let's see if CPU is powered. Okay, no power to the CPU. It's kind of interesting. There's power to the PCH, which is actually good. So it tries to do something, it's a little bit further to the power sequence. Let's do it once again. Okay, T2 booted. SSD power. Reads bridge OS. Bridge OS is loading. Ah, okay, we have now full power. So maybe it did check disk. Maybe it did check disk. So now let's go and try and see if there's some Apple logo or Apple sound from this machine. If it works, I will ask customer for the password, because the first thing you do is you back up your data. Maybe I won't have it, but you don't gamble, you just get data backed up, then you finish the repair, and then if something is wrong, at least you already got the data. First of all, customer will be much happier, even if it's not working. Second of all, then your work still will be paid lower price, obviously, because you didn't succeed completely, but at least you got data out. Okay, we need speakers, we need display. As I always tell, screw in display. So connector. So it's probably that it had some problem with NAND at the first, but it succeeded the self-repair, because low-level bootloader has some tools like FSCK inside. I believe it does something, like it fixes something. It's hard to know, but I seen logs from the debug version of this firmware, and it definitely has some basic possibilities to fix firmware problems and partitioning and system partition problems. Okay. Now let's plug it in and let's see. I have click, we have bridge OS loading, we have good power consumption, and we have audio. And we have Apple logo. Okay, now we're gonna turn it off and back up the data. So this is a very, very, very lucky case, because in many cases after you replace it even with working SSD, there will be corruption to the partition and you will not be able to get data. But this one is very lucky case. Okay, so I hope it was useful. I hope that it wasn't too long. Okay, well, 1 hour 22 minutes. But yeah, I tried to explain the whole thing. I will put a link in the description. Basically, it's WIKI. So next time probably we'll do a little bit further. So if we have the machine with some Intel CPU problems, we will look more. I think it also worth making CD3217 diagnostics video, because it's a little bit more difficult if you have 4 ports and how to diagnose, how to find the weak or broken port. But first I need to wait till I got the machine with such issue, so I can show the whole idea of using I2C diagnostics for such cases. But yeah, I think I'm gonna continue to do such videos. So this is not raw repair videos, this is like power sequence diagnostic video, and I hope it will continue. I will do it for M machines because basically there's not much useful information on YouTube and in pages, which might help people who started on Apple Silicon and still need to learn how to fix T2 machines. They are obsolete, but they are starting to be bread and butter of data recovery because they have value because of their data. Okay, so you have a nice day then.